Greetings, guys. How are you guys doing over there? I hope every one of you who are watching this are absolutely fine. And stay safe, guys. Even though we are in the post-COVID era, yet we have to be cautious all the time. So let's move on into my sharing today. So how many of you knows about STA? STA stands for Static Timing Analysis. And those who are new, welcome. And I would love to actually share how does this STA gonna influence our design. Mainly, let's go into the definition of STA first of all. STA means static timing analysis. So this static timing analysis is to actually evaluate every single timing performance in the design and making sure there is no timing violation across the design. That is the reason we wanted to actually have this static timing analysis. It is very, very important checks among any other checks. Obviously, in physical design or IC design, every check is essential. If you miss out one or two, your chip might not actually work. But most importantly, this major area, which is static timing analysis, is very, very important in order for you to make sure your design works well. On top of that, I've actually talked about PPA. Why this is actually important? Because in the PPA itself, already mentioned performance. So it means that it is one of the important criteria in IC design. In fact, I've actually made a video previously that you guys might actually heard of power on also area, which is actually the trade-off of this performance. So let's check it out. What am I actually going to share today? So today we're going to actually talk about STA in the definition. We have already covered what does that mean. And then we'll talk about some introduction on the clock. And then we'll talk about flip-flop. FF means flip-flop. The flip-flop of the flip-flop terminology. And then we're going to talk about the equation and also the timing graph. So without further ado, let me straight go into the introduction of clock. So everyone has to understand how does STA works. And it's not how does STA works, and how does STA actually influence our design. So mainly since it is related to the performance, automatically it actually related to the clock. So where does this clock coming from? Everyone might be wondering. Oh yeah, exactly, that's true. So we wanted to actually evaluate all the timing part and making sure there's no timing violation. So where is this clock? So here it is. This clock is actually generated from a PLL. We call phase lock loop. And this phase lock loop, there will be a propagation in the top level design. And then we call this as a source latency. And then this source latency would actually go to a block A. And it may actually go to other block as well. We consider as block B. But let's not talk about any other block. It's going to be the similar propagation from PLL into another block. Then after that, it actually goes to a clock. So this is the sync point, and this what we call it as network latency. So this is source and this is network latency. Today we're going to talk about solely on network latency, and this network latency cause or influence your timing of your whole design. of each and every single block. So you have to really understand on that one part. And here it is what we call as a clock definition. Over here there will be stamp of on top of this pot or pin, and this we call a sink, and as usual this we call a flop. It is important to really understand what is the terminology whenever you try to actually understand or extract from any diagram. So over here I hope you guys have actually clear that where is the main source of clock coming from. Oh yeah, it is actually coming from the phase lock loops, and from there it propagates into a block, then from there on it actually connects to all other flops. So mainly today we're going to talk about everything related to the flops, only flops, and then we'll talk about the terminology, we'll talk about the equation, and we'll talk about the timing graph. And not to forget, there are a lot of factors that actually influence this SDA. It is never actually about the setup or hold checks. Yeah, that's another new terms that you guys have listened. I'm going to go there in a bit. So I hope you guys have actually understood on this part. So let's move on into the flops. So over here there will be a sorry guys, I think I'm out of ink. Just give me a moment. Oh, such a relief. I got my marker pen here. So it's a new marker pen, so I'm back here. So let's continue. So let's draw a flop over here. So this actually would be your FF1 and this would be FF2. Before I actually move on into this, let me explain to you SDA comes into two parts, which is very important on hold and setup. Everyone should really understand how does these two timing checks works. So this is considered like a timing checks. And on top of that, for you guys to have extra knowledge that normally by setup you can set maximum frequency from the design. So somehow people will be thinking, hey, how far my design can actually run. That's the reason we talk about SDA, the timing performance. So it is actually derived from the setup checks. So from there onwards, you would actually know, hey, my design can actually work at this much of level. And hold violation is actually, for the hold checks, it is actually independent to the frequency. So this guy is actually independent to the frequency. So everyone should really understand why on hold it is independent and setup it is actually dependent. Clear factor I'm going to actually explain later on, but maybe for now I would say hold it is because it is checked at the same edge level, same clock edge level, so same clock. And then for setup, it actually checked on the next clock edge. So that is the reason you are actually seeing the big difference over here. Alright, so move on. So right now we will talk about setup checks. Alright, so I hope you guys have actually following me so far. So on this part, so let's move on. We draw a sink. And this is actually a launch flop, and this is actually a capture flop, and then this is Q, and we draw a combi here. This is Q, E, this is D. Okay. Alright, so and then I've mentioned this is actually your sync point. And this is your sync point, this is actually your required time, and this is your arrival time. And then you have to understand the flow for this is actually your launch path, and the flow from here to here, we called it captured path. So you guys really need to understand first what is the launch path and what is the capture path, and this is actually arrival time and this is actually required time. On top of this, we will not actually see these pictures in your run or in your tools. This is like a cross-sectional view, but in timing report you would actually see this as a start point, and this is your end point. So you really need to understand, because when you actually try to read your timing reports, it will be another level or another phase of, or another part of for you to do the analysis, but the methodology is always to be same. So over here you need to understand who actually going to arrive first at this clock. So that is the main reason. That's why we call it the start point and end point. Whenever you are running in a marathon, you would actually have a start point and end point. So basically this is exactly the same. You are actually racing. It's just a race that actually from your start point to the end point. So over here you need to understand setup charts, the definition. You have to know that the data has to be stable before the next clock being triggered. You really have to make sure that means your data should not be very slow. If your data is actually slower than your clock, on the next clock age, then you're gonna actually have a setup violation. So it is actually important for you to know this. So the formula here that you can actually see that your required time has to be more than your arrival time. In other words, your capture path has to be more than your launch path. In this sense, it means that your arrival time or your launch path that actually coming here is actually faster. It has to be fast enough to make sure it is stable before the next clock age. Otherwise, you're gonna actually see a setup violation here. Once again, this is actually highly depending on the clock frequency. That's the reason you actually will be seeing your launch path over here triggered at the first cycle, and then your capture path will be checked over here. This is your T setup. So you will be seeing your path right over here. So right now let's move on and check it out. How is the formula going to be? So over here we're going to have a C here, a C here. So this we call it TCQ. This we call it T combi. And then there is no delay at this point of time. There's no skew at this point of time. Later on we will introduce extra of that in between, so that you guys have a picture of it. Or probably maybe I'll add. Okay, now maybe I add a buffer here, a buffer here, a buffer here. Maybe this is delta 1 and this is delta 2. But maybe for timing, let's not talk about that. So let's pick this capture part. So this capture part, you have to make sure that it is actually bigger than launch part. So you have to make sure that launch part has to be stable before capture part. So I'll make sure I'll draw another new one so that you guys have a picture. So right now this and this. So you have to make sure that this is actually your T setup. There will be a T setup for every flop. There will be a T setup and there will be a T hold. So you have to know that. So this T setup is your over here, T setup. Alright, let's move on and draw another new timing graph so that you guys have a clearer picture here. So since I've mentioned to you earlier that for setup checks, your timing check is actually going to be on your next clock edge. So over here is your timing checks for the setup. But then you have to remember, we actually have a T setup of X value or XY value. So it means that you have to make sure that the data is actually reached before this T setup value. So it means that you have to understand the captured part or the required time. The captured part equals to T minus T setup. So you have to understand this. This is how the equation is going to be. So it means that the data has to be stable before T minus T setup. And then how about the launch part? The launch part over here equals to your TCQ plus your T combi. So your TCQ and plus T combi. So in other words, your TCQ plus T combi has to be faster than T minus T setup. In a way, the T is TCQ plus T combi plus T setup. Actually, you know something, by doing so, you can actually, if you add up all these and then you add up all this, which is, I put it equals to Y, and this Y is equals to T, and then 1 over T is actually your frequency, and this is actually going to be your maximum frequency. But it is not to be only one part. You can actually go for a critical part and then you try to evaluate. Go for a few parts then and then try to figure out how do you actually set a maximum frequency. From there onwards, you already put a threshold that this is the maximum and this is how you're gonna converge your design. So over here, it is clearly explained that you have to understand your data. So your data has to arrive earlier before the next clock edge triggered. So this is the equation for T setup. But at the same time, if let's say you have a delay being introduced, that's where, if a delay being introduced over here, so now we have delta 2. If let's say the delay being introduced, there will be extra delay over here, which is delta 2. So then you're gonna add the delta 2 here over here. That's so simple. Then at the same time, we're going to add delta 1 here over here. And then you can actually say it your T skew. Immediately this is considered as T skew. Your T skew is your captured minus your launch, which you would get delta 2 minus delta 1. So actually introducing delta is actually very good in setup because it actually delaying your clock and then making sure your data part is actually reaching earlier than it. That's the reason in CTS we have useful skew command. This useful skew actually introduce delay, a lot of delay at the clock part to make sure that you meet your setup your setup check. So that is the main reason they are actually doing that useful skill. But not to forget, I would love to actually point it out on the PVT. You really need to understand what is this PVT about. P is actually process, V is actually voltage, and T is actually temperature. So you need to understand the whole timing is actually being influenced. Another factor being influenced is also PVT, which is your process, voltage, and temperature. So from there onwards, you really get to know there will be a variation of timing check will be done and also results. So over here, as we know, if let's say you want to make it a worst case for setup checks, worst case for setup check. Worst case for setup check. So when T is temperature is higher, your delay is going to be higher. Whenever your voltage is lower, your delay is going to be higher. Whenever your process is slow, then your delay is going to be higher. So you need to understand why we are actually having this as a worst case, because we are giving the worst performance to the maximum check. For the whole, we are giving the best performance for the data part check. So that's the reason all this will be actually seen as data part. You make it a worst so that be able to actually converge it at the most pessimism level. I hope I've actually covered everything over here. We covered how to actually do a checking on frequency. From here onwards, you can actually do a check on frequency without any delay being added. It will be easier. And then we talk about the formula for required and arrival, captured and launch. And then we talk about the timing diagram, making sure that the T setup, the data has to arrive before the T setup over here. And if let's say there a delay being introduced, you're going to add a delay over here. And then this is a capture part, and this is actually a launch part, not to forget. And then that's it. So if you guys have anything to ask, just ask right down at the YouTube link, at the YouTube command, and you guys can actually talk more. We can actually discuss more on that part. So I hope I've actually covered most of it over here. So as usual, if let's say a setup being violated, immediately what you need to do, either you add a delay cell at the clock, at the capture part, or you remove any delay being introduced at the combi, or maybe there is a long net, you can actually introduce it. Just imagine if let's say there is extra 2 combi without actually touching the clock. Do you think you can actually solve it? Yes, you can. There is a way where you can do a pipelining in between. It means that if let's say you have 2 combi, and you wanted to reduce, or you wanted to actually maximize the frequency, what you can actually do here is you can actually add a flop over here. So it means that this gonna actually connect to here, and this gonna connect to here. I'm sorry. So it's pretty simple. But then your data, let's say you have a D0 here, it would actually reach here later than this. That is the only problem that we would have. Maybe I will cover this maybe some other time. I'm just giving you a scenario. How can you actually see differently? It is never actually about adding a delay, shortening the path, or reducing any delay in launch path. So it is not only that, there are more things on top of that, but I'm just giving you an example to have a picture what you can actually see. The most important thing here is you have to know, making sure your capture part is more than launch part, your required time more than arrival time. In other words, your time, your period, your clock period has to be bigger than your launch part. You just imagine, are you sure with this amount of time you're able to converge in the setup timing. Sometimes your designer would actually tell you, hey, I wanted to have a 1 gigahertz of frequency, but do you think all the data part able to converge before the frequency of 1 gigahertz? So you just have to actually divide 1 over 1 1 over 1 gigahertz, and you get your T. So this T, you have to make sure whether are you able to converge before that itself. So that could actually give you a picture. Oh yeah, maybe this part we can't convert. So that's the reason you talk back to your designer and coming back, and that's where negotiation skills comes in. And then let's move on into T hole right now. So I'm going to actually wrap it off all. So let's move on into T hole. T hole is going to be a bit interesting, and also the equation pretty much going to be the same. I mean the terminology, I'm sorry. The terminology is definitely going to be the same, but the equation is definitely going to be different. So, as usual, once more, we'll talk about PVT. And then over here, first of all, you have to understand T4. So right now, we do T4, whole checks. Whole checks. So in these whole checks, you have to make sure that there is a minimum amount of time the data has to be stable after the clock is being triggered. It is actually after. If the data is actually stable before that, then you're gonna have a violation in your whole in the whole checks. So that is pretty dangerous. So let's put that into equation. How do we do that into equation? So when we do that into equation, your arrival time has to be bigger than your required time. In other words, your launch path has to be bigger than your capture path. So I think you guys have to really understand this. Your arrive time more than required time, your launch part is more than capture part. So you really need to understand this whole picture. So once you really understand this, then you would move forward. You would move forward and make sure that you're able to actually strive to the next level. So for launch part, I think before that, I think it's important for us to actually see it in a timing graph so that you guys have a picture. As I mentioned to you earlier, your launch part is here. This is your launch part. It's actually checked by the same H as well, which is this is your capture part. So this is your launch part and this is your capture part. So both of them are actually going to be checked on the same H. So you really need to understand that. So over here, a T-hole being introduced. So this one I put a variable of XY as well. So you need to make sure that this is your T-hole. You need to make sure your data arrive right after an amount of time after T4. That is actually very important. So that is the reason you actually would see your let's talk about your for the equation. We'll talk about launch path. Your launch path is going to be equals to your TCQ plus your T combi, and then your capture path is actually your T hole. So you need to understand, your capture path is your T hole. Then as a whole picture over here, you would see TCQ plus T combi, your launch path is more than your capture path, which is T hole. Yeah, so it means that your data is actually coming later. It's delaying with an amount of T hole, once T hole being has been met, then after that it has to arrive. So that's the reason you reach. That's the reason. So now, in other words, you just have to actually understand that making sure your data has to arrive later. If let's say the data arrive early, then you're gonna actually have a whole violation. If let's say you have a T-skew here, so if it is a T-skew being added, then you're gonna actually hurt your T-hole. So for this case, we're gonna actually add delta here, TCQ plus T combi. We're gonna add a delta here, delta 1, and then T hole. We're gonna add a delta 2 here. So it means that TCQ plus T combi. Okay, alright, yeah. So you're gonna have this is the equation. So yeah, so in other words, if let's say your delta is bigger than your delta 1, then do you think you're gonna hurt or not? Definitely. It's because you are actually delaying your clock over here. You are delaying your clock over here. So let's continue. As I mentioned earlier, it is correct. So whenever delta 2 is actually higher than delta 1, so it means that this is a positive skew. Whenever delta 1 more than delta, this is negative skew. So whenever you're actually having a positive skew, it means that you actually gonna hurt your T hole. But whenever you're having a negative skew, you're gonna actually have a better T hole over here. So right now, if let's say delta 2 is actually more than delta 1, it means that you are making your clock slower, and hence hence the T combi part, which is the launch part, is actually going to be faster and going to hurt this whole process. So that's the reason maybe you can actually do this TCQ plus T combi, T hole plus T skew. So if let's say this whole process is more than this, then it's going to actually violate the whole check. So the whole pictures over here, everyone has to understand is making sure that you really understand the arrival time has to be more than required time. The arrival time has to be, because the data has to be stable for an amount of time after. It should be after the required time. It should be after the capture part trigger. It's not before the capture part trigger. So you have to understand this, because that is the reason we are actually having this. Both of them are actually at this are checking on the same edge. So it has to be your data of your launch part has to be later. This is your launch part, has to be later after the T hole. So this is the picture that I'm actually trying to give. You really need to understand. So because it is checked here. So whenever it is actually checked here, because you want to make sure that it comes later. But if let's say it comes before that itself, that it means that it's actually violating your whole violation. So I hope you guys have actually roughly have an idea what is actually going on over here. And moving on into this PVT, so let's talk about this PVT. So this is actually process, voltage, and temperature. So on this part, we wanted to have a best performance for the data part. So whenever you wanted to have a best performance, you have to make sure your T is, the temperature is actually colder or lower, your voltage is increased, and this is actually fast. And all this would actually give your delay slower. I mean your delay will be your D would be lesser, because when you have more delay, it means that you are having more time. So this, you're actually making the design faster. So I hope I've actually covered most of it for this, and making sure that you understand the check for whole check, it check on the same clock edge. For timing, for setup, you are actually checking on the subsequent clock edge, as I mentioned earlier. And then what happened if, let's say, a delay has been introduced in the clock part? If it is more, then it's going to actually violate. If it is less, then it's pretty good. So that's the reason in CTS stage you actually introduce useful skew a lot. And then later on the post CTS, tools actually would try to fix your code. That's why you would see more buffer being added later on. So that's where your whole violation actually fixed over there, but then it actually create your power dissipation increase, your area increase. Obviously, the area increase does not mean your floor plan increase. It means that your utilization rate keep increasing. So it depends how much utilization you have with the design and how much you have actually allocated at the beginning, and then later on how much are you actually allocating later on stage. Okay, so I hope pretty much I've actually covered everything here. I did not miss anything. And most importantly, if you guys are actually wanted to know more details, I think there's another one more part that I feel it is important, is on the files, which is the collateral of SDC and also CC op spec. And then you have to know your CTS exception as well. I think all this is actually very important for you guys to know. So for SDC, you really need to understand from how is your what version being actually set, what is the unit metric is being set. There are actually about 10 types. Maybe why not? I actually just introduce it here. Let me just rub this off. Okay, so let's talk about SDC. So SDC, we have measurement definition. There is a measurement definition here, and then we talk about there's a measurement definition here. Then after that we talk about timing constraint. Then we talk about design rule constraint. Then we talk about timing exceptions. Then we talk about operating condition. Then we talk about wire load. Then we talk about any area constraint needed. Then we talk about multi-voltage constraint. Then we talk about logic constraint. Yeah, I think this actually optional. This is actually optional. It depends. Normally, whenever you have this multi-voltage constraint, it is defined in your UPF itself. It should be defined in your UPF. And then the area constraint, if let's say this area constraint not much being actually added over here, but then you can actually do it in floor plan itself. So this is more into floor plan itself. But logic constraint, just want to make sure that you don't want to insert any small cell. So that's the reason we have this logic constraint. As usual, wire load, you would actually have large, small, and then so this is the wire load. So maybe you can actually extract by QRC as well. And then we have this operation condition, timing exceptions. We have false part, we have MCP, we have set case analysis over here. And design rule, we talk about max fan out. Then we talk about max fan out, then max trans, max cap. Then for timing constraint, you'll be talking about, this is the most important thing, which is your create clock. Then you have generated clock. Then group path. Yeah, so I think yeah. So we have timing conception, operationalization, wire load, area, and this. Yeah, this is something that's very important. And the measurement definition, you try to set your metric. Set your metric, which is on your voltage, current, your resistance, your capacitance, and your time. So what kind of metrics did you want to use? The value metrics of it. So so right after that, I think pretty much that's all. Once you really know, because sometimes certain part might not actually valid. So that's the reason we actually set false part. Maybe certain part can't actually be made within one cycle. That's why we need multi-cycle part. We need more part to actually meet the timing. And then set case analysis. Maybe you might actually have some boxes that actually intention one that you wanted to set case analysis. So there are more timing exceptions to it. Okay, so I think, yeah, pretty much that's all that we actually need to know on the SBC part. I hope I didn't actually miss out anything. If I actually missed out something, maybe I would actually try to type something later on, but I just wanted to add up something extra. On top of that, you would actually see on CTS CTS exceptions. You really need to understand what is exclude. You need to understand what is ignore. You need to understand what is stop, and then you need to understand what is float. So this is actually exception. So making sure that whether the part has to be part of CTS, or it just only need to do a DRV fix, or it actually need to add some insertion delay. So this is actually pretty much the same, but float is actually adding delay. You adding delay. This you do not add delay. Do not add delay. So for ignore, ignore and stop should be the same. So maybe I'll draw a table for you guys. Probably you might actually part of CTF, DRV fix, insert delay, beyond propagation. So we have exclude. Whenever we talk exclude, so it means that everything is X. Whenever we talk stop, it is part of CTS. It is fix your DRV. Does not. Then ignore. It is actually ignore. Then after that float. This is part of CPS. You fix DRV. You do not insert, do not propagate, but this, it is part of CPS, DRV fix, and then you float, but then it does not propagate. So this is something that you guys have actually know. I think pretty much that's all from today. If anything else, then I will actually try to add into some other videos. Thank you so much, guys.